we present CANNER, Category-Agnostic Neural Object Rigging. CANNER is a fully automated and unsupervised approach that learns to discover a low-dimensional motion structure space for category-agnostic dynamic objects, using only deforming pairs of 3D objects. It requires no category-specific prior knowledge, and once trained, enables feat-forward structure prediction and interpretable and intuitive post-editing for unseen objects on a wide range of categories. CANNER is inspired by the observation that motion of generic deformable objects often lies in a low-dimensional space, despite the high complexity of the deformation itself. Traditional rigging exploits this by using skeletons as an abstract of motion structure. However, it relies on extensive manual effort and expertise, and requires strong supervision from annotated data for models to predict. Limited by these factors, predicting rigging skeleton for new and rarely seen and unannotated categories is highly impractical. In this work, we tackle the problem of automatic discovery of motion structure just like rigging. Our target solution should meet three requirements. First, the structure representation should be flexible, which can be used to represent category-agnostic objects without prior knowledge of the category itself, and should be general enough to work on a diverse set of categories. Second, the training process should be unsupervised, using only animated 3D object sequences without human annotation or even correspondence between frames. And third, once trained, the model should disentangle the objects into spatially grounded structures, and have explicit meanings that can be interpreted by human. To this end, we propose to use a set of feature-embedded blobs as a unified representation. For any category, whether it's bear, fish, or even non-living things like glasses, they are all encoded into a set of blobs as structure representation. The blobs can be further moved around and edited to result in new poses and shapes. A decoding process would reflect these edits and output a mesh corresponding to that change. Note that the encoder and decoder share the same underlying architecture for any object category, so to create a new rigging model, we only need to fine-tune the weights on a few animated sequences on that category. Since the blobs cannot be supervised by available labels, we propose to define each blob with two separate groups of parameters. Pose-related parameters including position and rotation, and identity-related parameters including scaling, opacity, and an embedded feature that encodes the local shape of the blob region. Once we divide the two groups of parameters, we train the network on the task of single-instance pose transfer, where we use the pose-related parameters of one input to repose the identity extracted from another input. Using this training scheme, we do not require ground truth supervision of blob parameters and guarantee they are learned to disentangle identity from pose information in an unsupervised manner. Our method pipeline consists of an encoding and decoding process. To predict blob parameters for an input point cloud, the encoder first extracts pointwise features with semantic meanings and cross-attach them with a set of learnable query tokens, which are shared across all inputs to generate blob features. A group of MLPs then map each blob feature to its parameters. Once generated, these blobs can be edited by users to adjust the object's shape and pose. To decode the blobs back to an object mesh, the edited blobs are first voxelized into a feature volume and then mapped to a 3D occupancy volume using a transformer architecture. The volume is then queried with sampled 3D coordinates to predict corresponding occupancy values, which are then used to extract the edited mesh using margin cubes. To evaluate our method against baselines, we utilize a group of input and output point cloud pairs which have different poses. Given an input point cloud, we first predict rigging representations using each method, optimize their rigging to best fit the target point cloud, and evaluate the distance between the fitted target and ground truth target point cloud. This measures the plausibility and accuracy of the predicted motion structure for each method on the best possible scenario. As seen in the comparison, implicit methods like NDG fails to preserve object surface after deformation. Key point-based methods like KPD fails to model large deformation, and skeleton-based methods like ski-rig does not predict reliable skeleton for all object categories, resulting in implausible deformation. We show result on the effect of different editing modes on blobs. Moving certain blobs would animate the corresponding object part without changing the other regions. Scaling a blob would expand the local shape, and removing a blob would remove the corresponding region. We also show a failure example where moving the blob out of the expected motion distribution will lead to artifacts in the result. To show the temporal consistency and smoothness of blobs and animated meshes generated by Canner, we show results on the testset portion of Deforming Things 4D, an animated quadruped dataset. It demonstrates the spatial and temporal consistency of Canner-predicted blobs and meshes, despite it being trained only on object pairs. We show additional results on more categories, including fish, eyeglasses, and refrigerator, demonstrating the generalizability of Canner to diverse categories. To demonstrate the application of Canner on real-world objects, we capture a real-world category called Clay Monster, with 12 clay figures scanned in 35 poses each, using only an iPhone. Using this simple scanning pipeline, we are able to train our model for pose manipulation of such artificial clay monsters. Another interesting application of Canner is unsupervised and motion-aware point cloud segmentation. Since Canner optimizes a set of shared quirk tokens where each token corresponds to a specific region of an object, it guarantees semantic consistency across the entire category. We visualize this motion-aware segmentation by finding the dominant token with the maximum weight in a weight map for each input point. The results demonstrate strong motion awareness and consistency within the same category. Thank you for watching. Feel free to visit our project webpage for more details and cool interactive demos.